We've already talked about DFA and NFA conversion and subset construction, but one thing that has not appeared yet in the examples I've shown is how to deal with NFAs that have epsilon transitions. And so expanding on the previous discussion, in this video we'll talk about epsilon closures. Remember, every NFA has an equivalent DFA. Every DFA is an NFA. And because we know these two facts, then the class of languages recognized by DFAs and the class of languages recognized by NFAs are the same class. And as well, regular expressions can describe the same languages. So we have here the class of regular languages. And really the big kind of point here is that adding guessing to the DFA model does not increase the power of that model. To show how DFAs and NFAs are equivalent, it was pretty straightforward to go from DFA to NFA. For NFA to DFA, we've been talking about the subset construction. So just to quickly recap, the idea is that you make sets out of the original states. So here we had Q1, which was the original start state, and I'm going to just put some braces around that and turn that into a new state. And I can see that on 0, it goes to Q2, or it goes back to itself, and therefore the state that I send it to is Q1, Q2. Subset construction also has you build these sets up based on what you see in the right-hand columns. Since I see Q1, Q2, and just Q2 for 1, I'm going to create a new state called Q2, and I'm going to say, hey, I saw that, so now it's taken care of, and I'm going to create another state called Q1, Q2. And I saw it, so I'm happy, I'm going to take care of that. And then I'll talk about what those get pointed to, and anything I've seen before, it's marked. Any of these new states now need to have their transitions described as well. So I have Q1, Q2, Q3. All right, took care of that. Let's build that up. Those are done. I need Q3, and that's done. And I have the empty set as well because that was one of the ones that I reached. So that's done. And then checking just this left-hand column, I see everything in the right-hand side appears in the left-hand column, so I've taken care of every state. So now I have created in this case, 6 states that I need for the DFA. And I can go ahead and draw this accordingly. Awesome. The only thing that I need to do when I'm drawing this, and I need to watch out for this, is Q3 was the original accept state. So Q3 itself here is another accepting state, and then also this state Q1, Q2, Q3 should also be an accept state. The others don't have Q3 in them and therefore are not accept states. How do you deal with NFAs that have epsilon transitions? So this particular NFA has an epsilon transition from state X to Y and W. The previous example that we saw had all the arrows defined, or it went to a fail state. But this one, somehow I have to say something about the arrows that are going to come from X to go to Y and W. That's where we're going to have to define something called the epsilon closure. The epsilon closure of a state is the set that contains that state plus all the states that can be reached starting at that state by following only epsilon transitions. Looking again at our example, E of X is going to be X because it's itself, and following along, I'm going to see as well an epsilon to Y and an epsilon to W, and so here I have X, Y, and W. On the other hand, the other states don't have any epsilon transitions, so you notice Z actually doesn't have any arrows, so the epsilon closure of Z is just Z. T has an arrow, but it's just on B, so E of T is T. V doesn't have any arrows, so it's itself. And similarly for here Y and W. Right. So notice one thing that's important to point out here is that the set contains itself whatever you define the epsilon closure on. While I really haven't made the distinction yet, there is this concept of an epsilon NFA, which is an NFA with epsilon transitions. Now, you can turn an epsilon NFA into an NFA without epsilon transitions by using closure. And as I just said, we epsilon closure a state Q by following all transitions out of Q that are labeled epsilon. In terms of regular languages, this means the class of languages recognized by DFAs and the class of languages recognized by NFAs are the same class, and regular expressions also describe regular languages, and because we can turn epsilon NFAs into NFAs, epsilon NFAs also describe regular languages. It has no more power than an NFA without epsilon transitions. Going back to the epsilon transition and how you might notate it, sometimes we'll see E to talk about epsilon closure or E close. So if you prefer to write E close, it's just longer. It doesn't really matter, but it might be tough when we are doing subset construction tables to actually fit that whole function name in. Let me show you an example of using eClose instead. Over here, we have the state P, which has epsilon transitions to Q and R additionally has an epsilon transition to S. So that means that the epsilon close of P is PQRS. Actually have four states here, P itself, Q and R because it has an epsilon transition there, and then S because there's an additional epsilon transition from R to S. The epsilon close of R is R and S, and for the remaining states there are no epsilon transitions, and so the epsilon close of that state is just the set containing itself. Right? And so, I mean, all we did here, this was just to illustrate that you can use eClose as the function instead of just E. More generally, you can talk about E of R, where R is a set. E of R is a set of states that can be reached by following 0 or more epsilon arrows from any of the states Q and R. So just to make this a little bit more clear, let's say that you had the states Q1, Q2 through QK. You can make the epsilon closure based on, well, first of all, you're going to have Q1 through QK, and basically unioned with saying like from delta of Q1 and epsilon, all of the states that you can reach by following an epsilon transition, and as well, yeah, it keeps going, of course, because if you have something that this goes to, you also have to add that state as well. I will point out a key property of E of R is that it contains all the elements of R. So right here, Q1 through QK, because those were the original states that we had. Any state in R leads to itself if you follow no epsilon arrows. Let's say we started with an epsilon NFA and we wanted to turn it into a DFA. We can do that using the epsilon closure with the subset construction. We've already talked about the subset construction, but now we're going to add something to it, which is basically at every step doing an epsilon closure. I'm going to go ahead and talk about the steps in general, and then to make things a little bit more clear, I'll go through an example. So to fill a table entry for an input symbol, you're going to use these steps. 1, ignoring epsilon arrows. Write down the set of states using that input from the states in the left column. So this is something that we've done already because we had no epsilon arrows to ignore. Then basically you're going to toggle and say we're going to compute the epsilon closure of this initial set. so when you calculate the epsilon closure, you are going to take whatever that initial set was, which might be R, and you'll go ahead and calculate all the states that are reachable. So think of this as like a toggle, maybe. You're in kind of the epsilon close part of doing subset construction. Whereas when you ignore epsilon arrows, you're in like another part of the toggle, which is just to think about the input. And this is the part that we have already seen. Okay, so you think about it as having kind of these two parts to it that you're switching between on every step of subset construction. Let's look at an example. I already wrote the full answer up on the slide for you to look at, but I'm going to show how to work through it with a table that has more columns to more clearly show what that kind of toggling action is. The first thing that I'm going to do as part of subset construction is I'm going to look at the input. Well, in this case, I'm starting, and the start state is 2, so I don't actually have any input, and the state that I'm going to put in here is 2. And now let's take the epsilon closure of 2. And the epsilon closure of 2, it looks like, well, of course, it goes to itself, and it also goes to 3 on epsilon. Now that I have 2, 3, I'm going to figure out what states I can reach to get to x, this is more like subset construction like we've seen already. So 2 on x goes to 3, and 3 on x goes to 4. Now we have to do epsilon close once again. So I'm going to do the epsilon close of 3 and 4. And so 3 doesn't actually have any epsilon transitions. It does include itself. 4 goes to itself, of course, and it also has an epsilon transition back to 2. And so we include 2. And if you kept following along, you would see 4 goes to 2, and then there's another epsilon transition that goes to 3. In any case, we've already included 3, so we have every state. So we're done here. Now, let's go back to thinking about the next state like we would do in subset construction. Oh, and by the way, I wrote this as 3, 4, 2 just because that was the order I thought about things. It's also totally fine to write 2, 3, 4. Depending on how you went about it, maybe you like to put them in order. It's a set. It doesn't matter. Great. And now that we have the set that we found here in the most left-hand column, we're going to say, okay, we've included that state. And now I'm going to take the epsilon close again of 3, 4, 2. And all of these states are included, so you say 3, 4, 2. And then there are no epsilon arrows or anything to worry about because this is literally every step state of the NFA. And now let's look at the things that you can get to from 3, 4, and 2 on x. Well, 3 goes to 4 on x. 4 does not have an x transition, and 2 goes to 3 on x. So I've written this as a 4, 3, and of course 3, 4, right, like it is up here is also totally fine. And let's go ahead and do the epsilon close of 4, 3. And because 3, 4 and 4, 3 are the same, we actually know the answer already from up here, and it's 3, 4, 2. And so again, I've already included 3, 4, 2 in the left-hand column, so I'm done. All right, just to sort of finalize things, since I have the subset construction of this NFA, I can see how to draw a DFA. So what I'm going to do is I'm going to take these states that are on the left-hand side. I have 2, and I have 3, 4, 2, which, since 3 was originally an accept state, this is an accept state. So I only have 2 states. And then I'm just going to look at the final thing that you could get to using all the epsilon closures, and I see that from 2, I go to 3, 4, 2 on X, and on 3, 4, 2, I'm also going to just loop back on X, and this is a start state. So that is my DFA that I developed via subset construction, where I did have to think about epsilon closures. So that's all I have for you. Thank you for watching.